Hello and welcome. This is Rashid Khan and you're watching my YouTube channel. In this video, we will discuss some of the past exam questions on the topic called radioactivity. Let's have a look at the first question. This question is about the types of radiation. It tells us that there are three types of radiations: alpha, beta and gamma. You need to recall they are all are ionizing. Number one, they are all emitted by unstable nuclei. Now it says, which statement describes all these radioactive emissions? Ionizing and emitted by stable nuclei. So this is something that's wrong. This is right. Part B says ionizing and emitted by unstable nuclei. This is correct and this is correct. So the answer is B. Next question, they've shown us a diagram and we have a Geiger-Miller tube in this diagram. The job of this equipment is to measure the activity. Okay. It says one radioactive source used in hospitals is technetium. Technetium is produced from the radioactive decay of molybdenum. Complete the following nuclear equation. So if you remember, we said the total for the top numbers on both sides must be equal. Got 99 on the left side, got 0 on the right side. The remaining will be 99. I've got 42 for the lower number. Here it is minus 1. I need to add 43 here, because if I do 43 take away 1, it will give me the same number as 42. Next question says figure 9 represents a decay that can happen inside the nucleus of an atom. So we can convert this information in a similar equation. So I've got protons, so I can write down P. It has a mass of 1 and it has a charge of 1. Okay, now this then changes into a neutron. Neutron also has mass of 1, but it has no charge, so the bottom number will be 0. Now it has to give out something. I can call it X for now, and I need to figure out the two numbers. I know the total for the top number on both sides must be same. I've got 1 here, I've got 1 here, so I'm going to put 0 here. Same applies for the bottom. The bottom number must be same, so I can say it will be 1. This is what we call beta plus, or we can say beta positive. So here it says which decay is represented in figure 9. The only option that's correct is C. Next question says other unstable isotopes emit alpha particles. Which of these describe an alpha particle? Alpha particle is helium nucleus and is written as 4-2. It has a mass of 4 and a charge of 2. Out of these three options, the only one that's correct is C. Next question says gamma radiation is a part of electromagnetic spectrum. When the nucleus of an atom emits a gamma ray, the number of protons in the nucleus and the number of neutrons in the nucleus do not change. That's important information, right? State how the nucleus does change when it emits gamma rays. So if I want to change this statement into an expression just like we have here, we can say I've got nucleus, let's say this is 57, this is 25. It goes into something called Y. The numbers do not change and it gives out radiation, which is, you can see the numbers do not change here, especially these ones. So I can say there is no change in terms of the mass or the charge of the nucleus, but this one is stable now. We can say, how does it change? We can say it becomes stable by releasing energy. This gamma wave is EM wave. Next question says carbon-14 is radioactive and has a half-life of 5700 years. So the moment I see this word, I'm going to say this means activity will reduce by 50% in 5700 years. So the number of radioactive carbon atoms in a very old piece of wood is found to have decreased from this to this. So the atoms have decreased, which are carbon-14 atoms, from this number to this number. Now they can't go from here to here straight away. They'll change in terms of the half-life. So I can say I'll start with 1,000,000 and my final number here is 125,000. I can say after the first 5700 years it will reduce by 50%, so it will become 500,000. Then another 5700 years it will then become 250,000. Then another 5700 years, and then it will become 125. So how many 5700s do we have? I've got 3 of them. If you multiply them, you'll end up with 171,000 years. So it took this long for this carbon 14 to reduce from this number to this number. Next question says, sometimes food can become contaminated with radioactive substances. Recall. Contaminated means becomes radioactive. It says, describe the harmful effects of eating food contaminated with radioactive substances. So if we are going to eat radioactive food, then what will happen? This radiation will be given out by this radioactive material inside our body. And we know radiations are ionizing, so they can cause cancer. So we can say here, food will emit radiation inside body. Then I can say radiations carry energy. Radiation carries energy, therefore can cause cancer. Rather than saying radiation carries energy, we can say radiation is ionizing. Next question. It says carbon 13 and 14 are isotopes of carbon. So the moment I see word isotopes, I can recall they have same amount of protons but different amount of neutrons. Remember, this top number is protons plus neutrons, the bottom number is protons. It says complete the table for an atom. An atom means electrons will always be equal to protons because atoms are neutral. So I can straight away say it has 6 protons, this one also has 6 protons, so the amount of electrons will be the same. But when it comes to the number of neutrons, all I have to do is I'll do 13 take away 6, that leaves me with 7. If I do 14 take away 6, that leaves me with 8. Could be important bit for your exam as well. Make sure you know this part, and the rest is all good. Next question. This question is about radioactivity. Radium-223 is radioactive substance. Radium-223 is an alpha emitter. Remember, alpha is most ionizing and least penetrating. Say the half-life is 11 days. So this means this many days will be required for the activity to reduce by 50%. It says a radioactive source contains 1.7 times 10 to the power of 23 nuclei of radium-223. Calculate the number of radium nuclei remaining in the source after a time of 33 days. Now I can't jump straight away to 13 days. What I'll do is I'll divide this 33 into portions of 11. So you will start with 1.7 times 10 to the power of 23. After 11 days, this number will reduce by 50%. So I can divide this number by 2. We'll get answer as 8.5 times 10 to the power of 22. Another 11 days, you divide it again, you will end up with 4.25 times 10 to the power of 22. You divide it once again, you will end up with 2.125 times 10 to the power of 22. Now you can see that's the total of 13 days. So it says the number of nuclei remaining will be 2.125 times 10 to the power of 22. Next question, it talks about fluorine 19 is a stable isotope of element fluorine. The element fluorine also has several radioactive isotopes. Describe one similarity and one difference between the number of particles in one nucleus of fluorine-19 and one nucleus of a radioactive isotope of fluorine. They're basically asking you about the similarity and difference. You can say similarity will be they have same amount of protons, right? You can say equal protons. Difference will be they will have different number of neutrons, different amount of neutrons. Next question says some isotopes are unstable. They emit beta negative particles when they decay. Explain how nucleus changes when beta negative particle is emitted. Now you can write it down in words, or you can write down the decay equation for beta particles. So I'm going to write down the equation. So I'm going to say, I'm just making it up, saying there is a nucleus which is called X and it is unstable. You can assume any numbers for it. I'm assuming 57 and 25. Then it will change into something called Y, and when this happens it will give out beta negative, which will be 0 and -1. Now you know the top numbers must add up to the same number as it is on the left. The bottom numbers must add up to the same number as it is on the left. So out of 57, 0 goes here. I'll still have 57. Then for the bottom number, this is -1. I will have to increase it by 1, so it becomes 26. So all I can say is protons increase by 1. Here I can say P plus N remain 1. Next question. Explain how neutrons enable a nuclear chain reaction to take place. Now this is about fission. What happens, this neutron is absorbed by uranium nucleus. Number 2, then what happens? Uranium becomes unstable and splits, producing 2 extra neutrons. Then these neutrons will enable chain reaction. Okay, so next question. Some rocks contain uranium when they are formed. Radioactive decay in these rocks produce radon gas. Now you have learned radon gas is radioactive, and this is the natural source of background radiation. Explain why people living near these rocks have an increased health risk from background radiation. Increased health risk, this is what we need to focus. We can say number 1, radon gas is radioactive. Number 2, we can say it can get released. If it gets released from the rocks, then you can say it can then get inhaled, and if that happens, then this will lead to cancer. This question is about atomic models. So here it says, early in the 20th century, scientists fired a beam of alpha particles at a thin gold foil. Figure 2 shows the main parts of their experiment with some results. So this is the Rutherford's experiment. It says, explain how the results of the experiment shown in figure 2 support the nuclear model. So we have to recall, what do we mean by word nuclear model? So nuclear model means positive concentrated at the center. And number 2 is most of the atom is empty space. So I can see on this diagram here that most of the particles went through. Few particles show little deflection, and then very few particles show deflection greater than 90. So we can say very few particles showed deflection greater than 90. This confirmed that positive is concentrated at the center. The evidence for this is that most of the atom is empty space is, we can say, most of alpha particles went undeflected. So I've got the observation and a conclusion. Observation and a conclusion. That would get us full marks. Next question. So this question is about radioactivity. Figure 3 shows a Geiger-Müller tube attached to a counter. The GM tube is used to measure the activity of source of beta radiation. So this means we are using this GM counter to measure the activity of beta source. So there's an aluminium sheet between the beta source and the GM tube. All this do, it will block beta particles, because beta particles can't pass through aluminium sheet. It says the aluminium sheet is taken away, the counter is reset to 0 and then switched on again. The new count is taken for 1 minute. Explain why the new count is greater than 268. So in this case we can say it is greater than 268 because in the absence of aluminium sheet, more beta particles will reach the tube. Okay. Second part says the beta source is then also taken away. The counter is reset to 0 and switched on again. The new count is taken for 1 minute. Give a reason why there would now be a reading on the counter. So you need to recall there will be background radiation. We can say background radiation will be detected. It says state the SI unit for the activity of a radioactive source. It is BQ. Next question. A GM tube is connected to a counter. A teacher places the GM tube near to a radioactive source. The student starts the counter and the clock at the same time and writes down the readings shown on the counter every 15 seconds. The student plots the reading with a line of best fit as shown in figure 10. So this is what they have. Counter reading on y-axis, time on x-axis. Says calculate the average count rate in counts per second. So if you look at this, what they are doing is this is same as y over x from the graph, right? So you will have to calculate. This means you will need to calculate gradient. Okay. Now I've got two coordinates. I've already selected them. I've picked up this and I've written the value of x and a value of y. So I can say this is my x1 and this is my y1. This is my x2 and this is my y2. So all I'm going to do is y2 take away y1 over x2 take away x1. This is the same formula that you use in maths. You just plug in the values, which is 1760 take away 400 divided by 120 take away 30. If you put this in your calculator, it will give you the value which will be your counts per second. Next part says the student says that the experiment must have been done carelessly because the data seemed quite scattered, that the experiment has not been done with care. The teacher claims such results should be expected in radioactivity experiment. Justify teacher's claim. You have to recall radioactivity is random process. Random process. Therefore, count rate will fluctuate. Next question. In a controlled chain reaction of uranium-235, which of these could cause a uranium-235 nucleus to undergo fission? You need to remember the requirement for fission is always slow moving neutron. Out of these options, the only correct is C. This question is important because they've merged two topics, radioactivity and energy. So here it says the kinetic energy of one of the particles released in a fission reaction is this much. So I can say this is the value of Ke. The mass of the particle is this much. Calculate the velocity, we don't know the value of V. So I've done my annotation, now I know I have to pick up the equation that contains these three variables. So I'll write down equation Ke equals half times m times V squared. I can now substitute values for the Ke. I'll put down 1.2 times 10 to the power of minus 11 equals half times 1.4 times 10 to the power of minus 25 times V squared. Be extra careful with this section here. Once you've done this, you can put this section in calculator. Once you put it in your calculator, the calculator will give you an answer of becomes 1.2 times 10 to the power of minus 11 equals 7 times 10 to the power of minus 26 times V squared. To get rid of this, I can divide both sides by 7.6 times 10 to the power of minus 26, 7 times 10 to the power of minus 26 is 7.0. This will cancel out and it will give me an answer for V squared being equal to 1.71 times 10 to the power of 14. If you take square root on both sides, you'll end up with an answer which will be 1309373 m/s 0.4. Next question says figure 4 shows a Geiger-Müller tube used for measuring radioactivity. Describe how teachers should use a GM counter tube to compare the count rate from two different radioactive rocks. Now, first of all, in this case, in order to compare the count rate, we will have to determine what is the individual count rate for the two radioactive rocks. So first I'll do GM counter is over here. Here I'll use my distance D and it will be fixed. Then I can put my radioactive rock here. So I'll say number 1, record reading on GM counter. A will be in the absence of rock and B will be in the presence of rock. Then I'll say to figure out the count rate, it will be value B, take away value A. Then you will say number 3, you will say repeat 1 and 2 with second rock, and then you can compare them, right? So this is important, very, very important, right? So make sure you know this. In your exam, who knows, a similar question might turn up, but that question might include something other than the radioactive rock. So they may change this radioactive rock to something else. This question is about uses of radioactivity in medicine. It says positrons are antiparticles of electrons. The photograph shows a PET scanner that uses positrons to locate the site of a brain tumor. Positrons are emitted by the radioactive isotope fluorine-18. The fluorine-18 is attached to glucose. The glucose is injected into the patient's bloodstream and collects at the site of the tumor. Fluorine-18 has a half-life of 1.8 hours. So we can see here it has a short half-life. Question says state one advantage and one disadvantage of using a substance with such a short half-life. So advantage would be it will limited exposure to radiation. Now this is with respect to the patient, right? So the patient will be exposed to radiation for a limited duration of time. Disadvantage is going to be it must be produced close to the facility. Otherwise the activity will fall very low and then this isotope may become useless. Next question. Energy from the nuclei of atoms can be used in medical diagnosis and treatment. Fluorine-18 is a radioactive isotope used in PET scanners for medical diagnosis. Explain why fluorine-18 must be close to the hospital where it is used. So the answer to this question is already given in the previous question. So I can say short half-life. Okay, number one. Number two, must be used as soon as possible once produced. Okay, that's what we have said, right? So it must be produced closed. Next question. Some tumors inside the body may be treated by using either alpha radiations or gamma radiations. So you have to recall the properties of alpha and gamma. Explain why the source of alpha radiation is usually inside. So if you're using alpha, it has to be inside, while the gamma radiation can be outside the body. So I can say, got alpha, this one is inside. If I have gamma, then it is outside. Question says, explain why. We can say here, because alpha has high ionizing ability, while, or I can say low penetration power, therefore it must be close to the tumor. So if it is outside the body, it will never give it will give out radiations, but those radiations will never reach the tumor. So that's why it has to be inside the body so that it is close to the tumor. When it comes to the gamma radiation, I can say about them, they have high penetration power. So even if they are outside the body, they can still get into the they can get into the body and reach tumor. This is the second question that we've looked at with respect to the use of radioactivity in medicine. Next question says gamma radiation is produced by radioactive decay. Alpha radiation and beta radiation are also produced by radioactive decay. Compare the process of alpha decay and beta decay. That's what we have to compare. It says you should include what each radiation is and what effect each decay has on the original nucleus. So what each radiation is and the effect on the nucleus. So I can say here, I can make two columns. The first one I'm going to say this is for alpha and this one is for beta. When it comes to alpha, it is helium nucleus. When it comes to alpha, it is helium nucleus. When it comes to beta, it is fast moving electron. Now I can write down their equations. I can say I've got a nucleus which is called X, and the numbers are 57, 25, it changes into Y, and this time it will give out alpha, which is 42. So when it gives out alpha, 57 will now change into 53, 25 will now change into 23. So I can now say, based on this, I can say mass goes down by 2. And I can say charge goes down by 2 as well. We can do the same thing for beta. I can say same nucleus like I made up here. You can have any number. You can have any numbers here, right? I'm choosing 57 and 25. You can choose, let's say, 67 and 30, but you just have to be careful with one thing. The top number has to be bigger, the bottom number has to be smaller. And say X, again, same nucleus. This time it changes into Y, but by giving out beta. What is beta? Is 0 minus 1. Now I have to work out the top number. So nothing has gone out in terms of the mass. The top number still remains 57. The bottom number will now change to 26, because if I do 26 take away 1, that will give me 25. So I can say here mass stays the same, whereas the charge goes up by 1. If you say this, you'll get full 6 marks on a question like this. In your exam, who knows, it might be alpha and gamma or beta and gamma comparison. You just have to follow the same method like I did here. Let's quickly have a look at the last question on this topic, and then we are done. This is now about the nuclear energy. This question says, compare nuclear fission and nuclear fusion as possible sources of energy for generating electricity using a nuclear reactor. Your comparison should refer to the differences between nuclear fission and nuclear fusion. So again, it's a comparison. I can make 2 columns, one for the fission and the other one will be for fusion. So I can first give reference to the first one. In fission, you have large nucleus splits into smaller nuclei. That's what happens in fission. In fusion, opposite happens. So I can say small nuclei join together to make large nucleus. Next, it says the relative advantages and difficulties involved in using these sources. So first I'm going to talk about the advantages. In this case, the advantage is it is already in use. So the advantage of this one is no radioactive waste is produced. Okay, now we can talk about, so this is advantage, this is also advantage. We can look at some disadvantages. In this case, it will produce radioactive waste. You can say radioactive waste is produced. I can also say there is always risk of accidents. In this case, the disadvantage is it requires extreme conditions, which include very high temperature and pressure, and these are difficult to achieve. We've done about 22 questions on this topic. I hope you'll find this video useful, and I wish you all very good luck with your exam preparation. Thank you.